Finance Core Topic 3, DCF, Debt, and VBA, Learning Objective Number 2. Compute the present value of annuities and perpetuities, both immediate and deferred perpetuities. So let's think about annuity. Annuities is a series of payments, not just one single lump sum. So here's an example. How much did you pay today? So in other words, what is the present value for a robot that saves your company $1 million after tax cash flow for 5 years, starting in 1 year? So it's going to be a savings of $1 million a year from now, $1 million 2 years from now, 3, 4, and 5 years from now. And you alternative investments, the things you could buy, provide a 10% rate of return. So that is a payment of $1 million received 5 times at an interest rate of 10%. I'm going to go to the spreadsheet, and I'm going to use the PV function. Type PV. Notice it gives me a hint what comes first. I have the discount rate, comma, number of periods, comma, and the payment of $1 million. And it gives me, let me make sure I got everything right. Interest rate, number of payments. Oops, I got that wrong. Let's try that again. Present value. Interest rate is right here, 10%. Sorry about that. The number of payments is 5 years, and the payment is $1 million. So the present value of $1 million received for 5 years, starting 1 year from now at a discount rate of 10%, is $3.79 million. By the way, we can verify that using the tools from the last section. If I take a present value of $1 million received 1 year from now, discounted 10%, so that's 1 million over 1.1 to the 1 power, to the 2 power, 3 power, 4 power, 5 power. If I add all those numbers together, the present value of those 5 payments, or that 5-year annuity, is 3.79 million, and that's also what I'm getting here. So this is a nice shortcut when you know that the cash flows are equal. Let's talk about sign again. Since I put in a payment of $1 million, I'm getting a negative present value. And this is actually a robot that saves $1 million. So in some sense, the million is an inflow. It's a savings. So you should be willing to pay an outflow of $3.79 million for a promise of receiving $1 million a year. So that's why this turned out as a negative number. But I could have put a negative number in front of here just to change the sign. So let's do another problem. If the robot costs $5 million, so that's a present value, right? Present $5 million today, so we could write that there. If the robot costs $5 million today, how much must the annual savings be to ensure it earns 10% rate of return? So now I'm going to solve for payment where my present value is 5 million, 5 periods at 10%. So it's going to tell me, what is that annual payment that gives me a present value of $5 million. So I'll go to my spreadsheet. I'm going to use the payment function. I need a discount rate, comma. I need 5 periods, comma, and it needs a present value. That's right there. And I'm going to close that. So the payment is $1.32 million. So the present value of $1.32 million for 5 years must be $5 million. And I could just verify that right here. If I just change this payment to 1.32, notice that this present value turns into 5 million. All right, problem 3. If the robot costs $5 million today and saves $1 million per year, how many years must it last? How many years of savings must you get to justify the cost? So I'm going to save $1 million a year at 10, and I'm going to earn 10%. I demand 10% rate of return, and I'm going to pay $5 million a year. I'm sorry, I'm going to pay $5 million today. How many payments of $1 million must I receive to justify that $5 million return cost today? Well, I'm going to use the payment function equals payment. I'm going to put in the rate, comma, the number, we're using the n per function, sorry about that. I'm going to use the number of periods function. So what's the NPER function? Go back to my spreadsheet. I'm going to put in the rate, comma, the payment, comma, the present value, that's the negative, that $5 million, and it returns 7.27 years. So I can verify that up here, right? I could put in the 7.27 years there, and notice that the payment is equal to $1 million. But, so what this is telling me is if this machine, or this robot can last at least 7.27 years, it justifies its cost. Problem number 4, how much would you pay today for a robot that saves your company $1 million annually for 5 years? And at the end of the 5th year, the robot could be sold for an after-tax salvage, so a resale value of $500,000. So it's much like this problem here. Whoops. This problem here, except at the end of the 5 years, you get another $500,000. So how much should you be willing to pay? Well, I'm going to still use my present value function. I'm going to put in my rate, comma, my number of periods, comma, the payment is still $1 million, comma. Now notice here, the FV and type, they're in brackets. So anything in brackets in a function means it's optional. You can leave it off. So if I leave it off, it just means there's no future value. However, now I'm going to put in an FV right here of $500,000. So if I click on my function f of x here, I have 10% interest rate. I have a number of periods of 5 years. I'm going to receive 5 payments of $1 million. And at the end of the 5th year, I'm going to get another payment of $500,000. So what my cash flows actually look like are 1, 1, 1, 1, and then $1.5 million. So I should be willing to pay $4.1 million for the promise of savings of $1 million a year for 5 years and an extra payment of $500,000. So it's important to think about the distinction between payment and FV. You only enter a payment if there's more than one of them. FV is just a lump sum payment at the final period of N or T. Let's do a franchise example. A franchisor charges franchisees an upfront fee. The franchisor will then provide services to the franchisee that cost $10,000 per year for 20 years. At the end of the 20 years, the franchisor will buy back the franchise for $50,000. What upfront fee, present value, should the franchisor charge today if they want to earn 15% of return, 15% annual rate of return? So let us think about the cash flows. From the franchisor's perspective, they're going to pay $10,000 a year for 20 years and then pay another $50,000 in the 20th year. So the interest rate is 15%. So what is the present value of these 21 cash flows? 20 payments of $10,000, 1 year apart for 20 years, and 1 payment of $50,000 20 years from today. Well, I'll use my PV function. Got my PV function where I have an interest rate of 15%, 20 periods, payment of $10,000, comma, future value of $50,000. So there's my, I should charge at least 65 million or 65.65K thousand dollars for this set of fees. Anything I charge greater than that means I'm going to earn a higher rate of return. Let's look at another example using annuities. A firm purchases and installs vending machines. What is the value of one vending machine? In other words, how much should they be willing to pay today? If it is expected to generate income of $12,000 per year for a life of 12 years, and they want to earn 15% annually, and there's no salvage or resale value. So let's think about the cash flows. They're going to receive $12,000 a year for 12 years. There's no future value in it, over that $12,000, and they want to earn a 15% rate of return. So I'm going to use my PV function equals PV. I have my rate, my comma, my 12 years, comma, my payment of $12,000, comma, and I could either leave that off the future value or put it in. And so I should be willing to pay, that's why it's a negative, these are inflows, these are outflows. I should be willing to pay $65,000 today for that machine. What if the income grows by 2% per year? So that's an interesting problem. So I'm going to get $12,000 the first year, but then I'm going to, that income, that payment's going to grow by 2% a year. So let's go to the spreadsheet. So what this means is in the first year I'll get $12,000, and then that's going to grow at 2% a year. So what is the present value? And this is called a growth annuity. It starts off at some value and then grows at some constant rate. So I could just take the present value of each cash flow 1 over 1 plus r to the 1 period, down to the 12th period, take the present value. But when you have constant growth perpetuities, in other words, it starts at some value and grows at a constant rate for a number of years, you can use a formula. And here's the nasty little formula. The present value of a growth annuity is equal to the payment. That's the $12,000. That's the first payment. And then you can see the equation here where the G is the 2% growth rate. The R is my discount rate. The T is the 12th year. The R, again, is the 15%. The G is the 2%. I can plug that formula in, and notice I did that there, and I get exactly $70,427 like I did doing all this work. So it's a nice little shortcut doing the present value of a growth annuity. All right, last couple things we want to talk about. One is, what if the cash flows aren't annual? They are monthly. So here's the last two examples we did with the vending machines. So I'm going to get $12,000 a year for 12 years at 15%. Either growth annuity or no growth annuity. What if it's $1,000 a month, not $12,000 a year? So it's still $12,000 a year, but the first payment is at the end of the first month. Well, I'm going to get a payment of $1,000 for 12 years times 12 months. That's 144 payments. That discount rate is no longer 15% per year. I need it on a monthly basis, which is 1.25% per month. That's the rate per period. And then I'll take the present value using the monthly discount rate and then monthly payment and the number of months. And what you'll see is it's worth a little bit more money because the cash flows are a little bit closer in time. $1 today is worth more than $1 next year. $1 1 month from today is worth more than $1 2 months from today. So the effect of that is I'd be willing to pay more for cash flows that come faster. So I'll go to my spreadsheet, look at that. I'm going to use the PV function. Notice actually that this is my 15% divided by 12. I'm going to use my PV function, put in my 1.25%, 144 periods for $1,000, and I'd pay $66,628 for that machine. And the last couple things I want to do is present value of perpetuities, and let's talk about the timing of the payments. So the first thing is perpetuities. So annuities are a series of cash flows that are finite, say 12 years or 20 years or 10 years. However, what if a cash flow is promised forever? So IBM is considering an acquisition of another firm, and the other firm's expected to live for almost forever. Or we'll just say it's an infinite, it's going to give us infinite cash flows. The merger is expected to return $10 million in incremental cash flows forever. How much should IBM be willing to pay today for the acquisition to earn a 10% annual rate of return? And again, remember, the first cash flow is $10 million received exactly 1 year from now, then 2 years from now, and 3 years from now, and on and on and on and on. Well, when you have a series of infinite cash flows, the formula gets really simple. The present value of a perpetuity is the payment received 1 year from today divided by R So 10% divided by 0.1 is $100. IBM should be willing to, be $100 million. IBM should be willing to pay $100 million for a promise of $10 million a year. And if they do pay $100 million, they'll earn a 10% rate of return. However, what if due to integration delays, the first cash flow starts 2 years from now? Well, here's a slightly different formula here for a delayed cash flow. So if the payment starts in year T, in this case year 2, what I do is take the 100 over the 10% and divide by 1 plus r to the t minus 1. So if the first cash flow starts in year 2, I'll take my present value perpetuity formula, which then will give me the value in year 1, and then I'll discount it back for 1 more year. So it just turns out to be that 100 there divided by 1.1 to the 1 power. So what if the 10 million starts, or the next problem here, what if that 10 million starts in 2 years and the cash flows will grow at 3% forever? So the first year you get 10 million, and then the second year you get 10 million times 1.03, and the third year you get 10 million times 1.03. I'm sorry, this one starts in 2 years. So 2 years from now you get 10 million. 3 years from now you get 10 million times 1.03, and so on. So the cash flows look like in period 1 you get 0. In period 2 you get 10 million. In period 3 you get 10 million times 1.03. In period 4 you get 10 million times 1.03 squared, and so on. So these cash flows then grow forever. Well, slight modification to the above formula, just plug in a G right there. All right, you can see it right here. So what I'm going to do is just use the same formula, 10 million over 0.1 minus 0.03, present value of a growth perpetuity, discount it back for 1 year, and I'd pay $129 or $129 million for a promise of 10 million in 2 years, and that cash flow then grows at 3% forever. And by the way, this is a general formula too. If it's a single cash flow of 10 million received 1 year from now, I can say the present value of a growth perpetuity that in which the first cash flow is received to 1 year from now would be that payment in year 1 over R minus G. Okay, last thing in this section, a note on beginning or end of period payments. So question, should you purchase or lease equipment? The purchase price is $10,000 due today and lasts 7 years, no salvage. Now, so that's the present value of purchase is $10,000 received today. Now here's a lease. A lease is going to be $155 a month for 7 years, with the first payment due in 1 month. The annual discount rate is 8%. So if I go to my spreadsheet, I'm going to have my present value put in my discount rate, that is my monthly discount rate, comma, number of periods, 84 months, comma, payment of $155 a month, comma, and I can just put no future value. So I should, the present value of the lease payments is $9,945, which is cheaper than the present value of the purchase, so I am going to lease. However, you read the fine print, what if the first payment is received today, still a total of 84 payments, 7 times 12. Well, slightly different. I'm actually going to copy this formula down. Whoops, I'll just put it in here. Equals PV rate, comma, 84 payments of 155, no future value. However, notice there's one extra fact. It says type. 0 is the default, meaning end of period. 1 is beginning of period. In other words, if you have payments and the first payment is received at the end of the first period, like we've done for every example here, we've used payments, you'd just leave it blank. However, if the first payment is actually received or paid today, put a 1 in there. when I do that, the present value, the fact that the 155 start today and not a month from now, so every one of those payments is a little bit closer, is 1 month closer. It's actually has a present value of 10,011. So if the first cash flow starts today, actually, I won't do it. I will stick with my purchase. However, if the first cash flows start a month from now, I will do that. So this was kind of an overview of how to deal with annuities and perpetuities and calculate their present values.